cover the full range of basically, how to get in and how to do all your work within Helioscope. So, starting from the very beginning and working all the way through. As far as applications go, Helioscope is really commonly used on projects that range from residential through commercial and all the way through to ground mount scale. So that's actually not a good one to use. So basically, the same tool is actually used on all three, whether you're laying out 15 modules or 1,500 modules. The best way to show that is to actually show all three. So I'm actually going to be starting with a commercial example just because that has the best of both worlds in terms of having the sort of scale of a larger system where you're laying out a couple thousand modules and still, kind of like having to manipulate and change those. But it's also got the rooftop, sort of smaller, where you do also care about shading, setbacks, etc. So I'm going to start again with commercial, but then I'll also spend time on a residential example, and then finally I'll do a ground mount one as well. If you only do one of those project types, I would still recommend watching for the whole webinar, just because the principles are similar, but sometimes applied slightly differently across all three. So from a learning point of view, even if you only do one of those three applications, it's still kind of worth it to kind of watch all three so you can get a really good understanding of how Helioscope works. As we go, don't hesitate to chat any questions to me. So I just typed hello into the WebEx chat, and I'm keeping my eyes on that. So as we go, if you have any questions or anything that you want me to review or take a tangent on, don't be shy. That's the point of doing these live. Also, as I go through, you don't have to memorize every single thing that I do. Just remember what can be done. So part of how I like to frame this is use this time to see what Helioscope can do. And then if you forget the details, know that we've got live chat. So if you have a question, then you could even say, I saw Paul copy a keep out. And then we'll be able to follow up with documentation on whatever it is that that you have a question on. So again, you don't have to memorize every single thing that I do. Just know that that there's something to be done, and then know that you can lean on us to provide the documentation that you need when you get to that point. Also, I am recording this, so basically this is being recorded now, and I'll record the whole thing and send a link to the recording afterwards, mainly so that again, I am going to move a little bit quickly to try to squeeze in as much information as possible, and if you want to forward to a colleague, that's also totally fair. So again, you'll get a link to the recording afterwards, so if there's a part that you missed, no worries, you'll be able to catch up on the recording. And then I do think it helps to just kind of start with a really high-level executive summary of what is Helioscope and how does it compare with other programs that you might be familiar with. So at the highest level, you can think of Helioscope as a cloud-based hybrid of AutoCAD and PVSys if you do commercial systems, or SketchUp and PVWatts for residential. It's basically a really fast, really efficient, really convenient way to figure out what's going to fit on my system, what's the production going to be given the location, any shading instructions, the weather, etc. And then it produces a bunch of outputs, including an energy yield calculation, single line diagram, AutoCAD export, bill of materials, etc. So it's kind of a bit of a hybrid of a design and simulation tool. From a user point of view, it's really a mix of both sales and engineers. A lot of the value of Helioscope is that this is a program that both the sales team and the engineering team can use. And so keep an eye on that, because there'll be a few things as I go through the demo in detail where I'll come back to that point where things are sort of automated such that the non-engineers can use it, but calculating the way that the engineers would want to be thinking about it. Anything from row spacing to setbacks to shading analysis. You'll see that a lot of the value in Helioscope is this is often the first tool that you'll have where both sides of the organization can use it, both sales and engineering. In terms of other things to watch for, the two most important things of Helioscope are, first of all, that ease of use, the fact that it's actually really easy to pick up, that both sales and engineers are going to be able to kind of use it. Essentially that the sales team is going to be able to get in and make use of it, and then the engineering team can go as deep as they want to. And then second of all, the speed of using Helioscope. So obviously the first design that I do, I'm going to go slowly to talk through what's happening, so that might take me 20 or 30 minutes. But then the next one I'll probably do in more like 5 to 7 minutes, and the third one I typically do in like 2 minutes. So you can do a design fully design and simulation in under 2 to 3 minutes, obviously depending on how much care you're taking. So that speed in Helioscope is a really big attribute as well. I mean, we consistently hear that we're 5 times faster to use than any other program on the market. So with that being said, I will start from the top. Now, any questions for me before I get started? And for anyone that just joined, if you have questions, don't hesitate to use the chat tool in WebEx to type your questions to me. Sounds good. And again, for the record, you can share your questions at any point, and I'll be keeping my eyes on that as we go. Cool. So let me start from the very top. This is the Helioscope homepage. This is the first thing you'll see when you log into the software. If you've got projects, they're going to show up here on the left-hand side of the page. The first step to doing any work is to create a new project. Every project needs a name. As far as the address, you've actually got a bunch of different options here. So if you have a street address, you can just type that in. So notice as soon as I type in 531, this used to be our old office, it'll take you to that location. Notice I don't have the zip code or city, so it doesn't have to be a sort of carefully done address. As long as it's enough for Google Maps to find it, you're going to be good to go. And so, it's pretty flexible for finding a location. In fact, if you've got a landmark, like for example Howard University, you can also find a location based on that landmark. So if it's got a unique enough name that there's only one of it in the world, then it'll work. So obviously if I just type Walmart, I don't even know which one it's going to take me to, but there's a lot of them. So it's, Google probably has some process for picking the one that I probably want. But yeah, it's pretty flexible if it's if you just have the name of a landmark, or if you have sort of a latitude longitude. So in fact, again, another documentation page we can share if you want to know is the exact format for latitude longitude. Bottom line, you want to be in a decimal format. So if I type in the decimal format here, you can find the location based on that as well. So if you're finding it in a different application, including Google Maps, you can also find the latitude longitude. In fact, this shows you exactly where to get it from Google Maps, and then you can paste that right into Helioscope to pick the spot there. And finally, you can also start at a location and then move the map. So for example, if I zoom out, and let's say I know that I'm northwest of Victorville. So I'm starting here in Victorville, California. I zoom out, and then I'm going to pan the map to the northwest to find the exact location that I want, and I can kind of skim around and then actually find it here. Notice this crosshair in the middle of the page, or in the middle of the image. That's actually going to be the latitude longitude reference point for the project. That project home is pretty important because that's kind of the 0 point for a lot of the calculations. A lot of the module distances, row-to-row shading, wire length calculations, etc., are calculated with respect to that point, which means that you want to stay within about a mile of that center. If you go outside of a mile, like believe it or not, the curve of the Earth can start to lead to errors in the calculations. So use that point and make sure you're in the same ballpark. So what that means is in practice, let's say you've got a university or a hospital where you've got a family of buildings in one area, then that can be a project, and we can do different designs across the different buildings, no problem at all. But let's say you're working for Walmart of Texas, you should create a different project for each Walmart facility. So of course, if a facility has a family of buildings, that's one project. But if you've got multiple ones in different counties, each one should have its own project. So now with that, we would create our project. I'll just jump to an existing one. By the way, Alex, I'll get to your question in just a moment. So now we've got the project created. This is that latitude, longitude reference point that I was talking about. Within the project, there's two main aspects of doing the work. There's designs and there's condition sets. Now each design is a sort of a complete physical build plan. So notice I've got a bunch of designs here ranging from 5 kilowatts to 500 kilowatts to 3 megawatts. And each one of these, if you open it up, is going to have a complete set of which modules you're using, bill of materials for electrical, inverter, and a picture of what you've got. So notice it's a pretty detailed design here of where the arrays are located and what we're building there, etc. So each one of these designs could be a different building, or it could be different iterations of the same building, and I'll show you how you can do that. Then the condition set is the environment around the array. So this is primarily the weather file. That, of course, makes a pretty big deal for what the overall energy numbers are going to be. But also, if you've got soiling losses, if you want to change the temperature modeling assumptions, if you've got mismatch assumptions, this is where those live as well. So those are sort of the environmental factors around the array. Basically, the design is the stuff that you build. Condition set is the stuff that you don't really control, but you can make different assumptions for how the world is going to go. And then the way those two things fit together, you can see right here. So let's say I've got a dozen designs and 4 condition sets. Then that means I've got 48 potential simulations that I could run, each one doing module level calculations every hour of the year. And so as this is simulating this specific design, it's probably about 2,000 modules, 1,800 modules. It's running through about 5,000 hours where the sunlight is non-zero. That's roughly about 10 million IV curve calculations that go into this, because we're calculating the IV curves for each module, each hour of the year. And then as a result, this simulation tells us what the array is going to produce. High-level numbers here, monthly values there, your loss calculations here, so you can help troubleshoot if the numbers seem high or low, and then your bill of materials and a picture of the array. So basically, that's the high-level structure. So project gets you started. A design is the physical array, so you need to create at least one of those. And then you go to the Reports tab to run the simulation for the design that you created. By the way, I made a brief reference to it, but just to point out, when it comes to the physics, we've got the exact same math as the PVSys has. We built it ourselves, but it is within a 1% tolerance. We actually have a third-party engineering report kind of proving that. So basically, the numbers that you see here are the same numbers that you would get in PVSys. So now let's actually go in and create a design here from scratch. I'm actually just going to delete a couple of these to clean up my project here. Sorry, let me just clean this up. Okay, cool. So now I'll create a new design here, design 25. So now we're here inside the designer. Now the first thing that I like to do before actually creating my design is actually first to just try Google and Bing. So basically these are both satellite images. We pay for both. You've got the options of which one you want to use. So in this case, it looks like Google is better than Bing, but I've increasingly heard from some folks that in some regions, Bing is getting better, and it's a respectable second option to Google. Now, if you have a Nearmap account, then you can integrate that with Helioscope here, and as you can see, that'll just show up as a third map layer. So Alex, to your question, yeah, you would need to contact Nearmap for both a trial and eventually to purchase a subscription with them, and then you would just link the accounts together under your Helioscope account, and then your Nearmap data is just going to show up here kind of fully integrated with Helioscope. Now, so obviously that's great if you've got the budget for it. It's a really nice combination of their high-res imagery and our kind of powerful design program. For the sake of the demo, I'm going to go back to Google just so that I'm using the standard, standard imagery that you get for the $95 a month Helioscope license fee. Just know that it could be even better if you also have the budget to add on some Nearmap on there as well. So now we've got our initial building, and I'm going to start the design by creating, by starting the mechanical step, creating a field segment here. So I click the orange button to create a new field segment. I'm now clicking the points, the corners of the shape to define the shape. Notice, by the way, if you hold Shift, it'll keep this line perpendicular to the previous line. So basically, in that case, and it'll actually snap it when it comes back to the point that's perpendicular from the first point. Then and then you can either click and then bring it back to close the shape, or I could have double-clicked that fourth point as well. So now we've got our shape. Now we select a module. This is a search bar. We've got over 44,000 modules. So if you're looking for a Trina, 335, notice just search for the manufacturer name and the power. So Trina 335, Canadian 350, whatever. And then notice for many of these, we're going to have a 3, 5, a dozen different modules that match that. The key thing is don't try to match the name in detail, because often when they're entered, they might be entered with an extra space or with an underscore. And so if that naming is inconsistent, if you're typing with an underscore or a space instead of the dash, then it can come back and say no results. Whereas instead, just type the name and the power, it'll give you a short list, and then you can pick the one that matches the actual specific module that you want to use. So with that, I'll just use an LG 360, and you see that initially we've got about 2,100, or just shy of 2,200 modules, about 778 kilowatts. Now, next, of course, you can see that the modules are filling up to the very edge of the shape. So that's, of course, not very realistic. To fix that, I'm going to go to the bottom of the mechanical mode for the setbacks, going to give myself a 4-foot setback around the perimeter, and so now we've got our 4-foot setback all around the shape. So now we've got, we lose about 150 modules down to a 729 kilowatt rooftop. Now let's look at the orientation. So the modules are facing south. That's the default because I'm in the northern hemisphere here. So the azimuth of 180 means the modules are facing south. So if I just type in a different number, say 210, then you can see that they're going to, point southwest, facing the southwest angle. So this follows a compass. 270 is west, 180 is south. It's also a great reason to show the 3D view. So we already have a 3D view because the modules have a tilt. So watch this. If I hold down the shift key, you might have heard that in the background, and I drag the mouse up, it's going to tilt the view. Drag the mouse to the left, and it rotates the view. So if I now zoom in, you can see that, yes, the modules are tilted up towards this as the front kind of, the front corner of the array. It's pointed towards that corner. Then I'm just going to hit recenter, and it snaps me back to the top-down view where up is north. So back to this, with my for the azimuth, the better way to do it, instead of just typing different values in here, I can actually set it automatically. So notice that every line segment has white circles at the corners and a gray circle in the middle. If you right-click that gray circle, it's going to give you the option to set the azimuth to 174 point, or well, in this case, 174.3. That specifically is the azimuth at which the modules are facing that edge. So let me again kind of rotate the view so we can see that, yeah, they are facing that edge. Again, it's a very slight 15-degree tilt, so it's not, crazy, but but you can totally see that. So basically, you can use that to set the way the modules are facing within the shape, so that they're going with the building as opposed to just some random direction. Again, the kind of thing where it sort of gives you the sort of engineering, or I should say, sales team level of kind of patience, but engineering team level of output. Next, let's talk about row spacing briefly. So I've got, obviously I've got a single row of modules, then a gap between the row. That gap is based on the row spacing right here, which is currently set to 2 feet. Now that 2-foot row spacing results in a span to rise ratio of 2.3, a ground coverage ratio of 0.63. If you're not familiar with what those are, it's a great excuse to pull up our embedded documentation. So we've got overviews on things like the racking, frame sizes, and in this case the row spacing, where it actually shows, you can see what the span to rise looks like and what the GCR looks like. So obviously the span to rise is just the gap versus the height. GCR is the ratio of, the land area versus the module surface area. So in other words, with a 2.3, for every inch of height here, I've got 2.3 inches of gap in between. With a 0.63 GCR, for every acre of roof surface, I've got 0.63 acres of module surface area. Now what's interesting is, so first of all, if I change the row spacing, say from 2 feet to 3 feet, you can see the module layout changes. You can see we lose about 300 modules here. And then the span to rise ratio increases and the GCR ratio decreases, both of which make sense if you kind of think about what's happening. The other interesting thing is you can work backwards. If you want to target let's say a 2.5 GCR specifically, you can just type that in, and then Helioscope calculates the row spacing to be 2.15 feet to get me that 2.5 GCR. I'm sorry, 2.5 span to rise. If GCR is how you think about things, that's also perfectly fine. So 0.57 ground coverage ratio, type that in, and my row spacing moves to 2.59. So it's totally up to you in terms of what, which lever is the one that you use when thinking about your business. But whichever that is, you and your team can be using that when you're setting the design from the very beginning. Oh, and by the way, there's a fourth way to set the row spacing, which is based on the time of day. So this says, on the winter solstice from 10 to 2, notice everything is configurable. Calculate the sun's angle in the sky. Calculate the shadows that are going to result from my modules at that day and time window, and give me the row spacing to be as close as possible while still not going, while not having shade in that day and time window. So as a result, we've got row spacing of 1.59 feet, actually giving us an even bigger system of about 2,200 modules. So again, notice that time of day spacing is going to be based on where you are in the world, right? Because it's based on the winter solstice from 10 to 2 at each exact spot on the planet. So that it goes back to that original latitude longitude reference point that feeds into the time of day calculations here. So basically the further you get from the equator, the longer the shadows are going to be, and therefore the wider the row spacing is going to be. So that's our initial layout here. So with that, we got about 2,200 modules. Like I said, I took my time a little bit just to explain what was happening, but hopefully you can see that if I wasn't talking through what I was doing, this is like a sub 1 minute task. So let me pause for one more moment. Any questions so far? Otherwise, next I'm going to go into keep outs and start to design for the obstructions. All right, sounds good. So next, obviously we have some obstructions on the roof. So I'm going to design around those using these keep outs. So go to the keep out menu. This is also where this button becomes helpful. Notice that we can hide the modules so that we can see what's underneath them in order to draw the keep out. Also, if you notice, there's a hotkey of shift spacebar, so I'm going to start to use that as my hotkey here. So in this mode, with the keep out selected, we're in drawing mode. So just like with field segments, I'm just going to start to click points on the map. Also, as before, I'm going to hold down the shift key to keep these on perpendicular, and it snaps the last one, and then I double click the last one to finish. So with that first initial keep out, if I then hit shift space to toggle the modules, you can see that by itself that's going to remove 4 modules. Okay. Now, you can see though that some of the modules are actually pretty close, maybe closer than I would like. So you also might say, let's add a 3-foot setback on all sides just for sort of maintenance. You know, this thing's going to break down at some point. I want to make sure we've got the maintenance clearance so that the maintenance team can access it. Now we go from losing just 4 modules to losing, it looks like more like a dozen or 14 modules. And then finally, you can see that it's casting a shadow. So it can actually give it a height. And so if I give it a height of 5 feet, check out what happens. Helioscope gives this HVAC unit a 5-foot height. It calculates the shadows based on, again, the winter solstice 10 a.m. to 2 p.m. And it treats those shadows as a keep out. So what you see here is the shadow that this object is going to cast on the winter solstice from 10 to 2. It's based, once again, on this exact location on the planet, so you'll get a different result here depending on your latitude, longitude. Not to mention if you're in the southern hemisphere, then obviously the shadows will go to the south. And then, yeah, you can treat those modules and basically remove those automatically. So now we're missing, what is it, about almost 20 modules or so. By the way, I'm going to come back to the shading because that's not the only way to think about shading, but it's a nice sort of clean, conservative way to get started. Now, to do the rest of them, I'm going to start to copy the keep out. So the way I do that, again, I hide the modules. Now I'm going to go into edit mode. So notice I click this pointer to go into edit mode. And now I'm going to hold down the Alt key or the Option key on the keyboard as I drag this object over, and that copies the keep out entirely. So in that way, I can now quickly copy multiple keep outs here for all of these HVAC units on the roof. So basically, it's actually just like PowerPoint. So anyone that is a PowerPoint or Excel user, the exact same thing. Hold down the Alt or the Option key to copy an object, and you copy that object entirely. And so now, instead of having one HVAC unit, we've got 10 of them, all in the right locations. Now at the top part of the roof, I'm going to do something slightly different. Up here, I'm going to say, look, I've got some vents, so let's just stay clear of the whole vent up here at the top. So I'm just going to create one big rectangle. Around that rectangle, I don't need a setback or a height because this is just an area that I'm just going to use some judgment and just clear out from the area. I'll do the same thing at the bottom part of the roof, big rectangle down here. And basically these are sections where I'm just saying, look, I just want to stay away. There's a bunch of obstructions. I'm near the edge of the roof. It's just not worth it to try to squeeze in there. And the broader point is that you can be using keep outs in different ways. You can use them for very specific physical objects that have dimensions, clearances, heights, and shadows. Or you can use them for sections of the array that you don't want modules in for any reason at all. Maybe it's aesthetically. Maybe it's the roof can't handle the weight load. Maybe you've got some watershed issues for a ground mount system. All of those are good uses of a keep out. In fact, you can also use a keep out for a walkway. So watch this. If I click once on the left, double click on the right, that straight line is going to remove the modules. If I then want to be a little bit more careful, I can apply a 2-foot setback around my straight line. And in the same way that here I've got an object with a 3-foot setback around the object, well, my object is a line. A 2-foot setback gives me a 4-foot wide access path through the array. Let me do the same thing top to bottom. Click once on the top, double click on the bottom, and I've got my 2 walkways for, say, CAL FIRE access regulations. If I also want to add additional ones for maintenance, I can do that too. Here, the key thing to notice is that as you add multiple objects, Helioscope assumes that each object is going to be like the previous object. So in this case, all of my keep outs are inheriting the same 2-foot setback that I just set for the first walkway. So basically, if you batch up your work like I just did, then you don't have to type in 2 feet for each one. Oh, one small thing here, I kind of messed this one up. So notice it's kind of like off-centered. So it's really easy to just go to edit mode, drag this over, and just kind of square it off so it's not removing two sets of modules there. Cool, easy to fix human mistakes. Great, so now we're kind of done with the first rooftop. Good question from Alex. I will also come back to that question. Now, before I finish this, let's just make it a little more complicated. Let's say that down here is a neighboring building that might be 50 feet taller than our main rooftop. So for that, if we want modules on that neighboring building, I'm going to add a second field segment. So go back to mechanical. Let me go in here and start my field segment shape here. Great. So now, again, with the initial keep out here, with the field segment here, notice it's just like I was saying about multiple keep outs. The same thing applies to multiple field segments. When I draw my second field segment, Helioscope takes a guess that I want the same module, the same orientation, the same tilt, the same spacing, which is a good guess, right? This whole building is facing the same direction. But let me change a couple things about it. The racking, if you notice, is fixed tilt racking, which means that it's facing south. You know, like you can kind of see it here. It's pretty straightforward. I could also try east-west racking. You notice if I do east-west racking, you get these little, the little kind of dual tilt modules, the little tenths of modules. Typically, that's a shallower tilt, so I'll make that a 10-degree tilt with tighter spacing. And so now I've got something that looks more like an east-west layout. And also, I said that the nearby building is a 50-foot tall building, right? So here is this height parameter that I haven't yet touched. So if I make this a 50-foot tall building, notice what happens. In the same way that this 5-foot tall HVAC casts a shadow on the modules behind it and removes those modules from the array, this 50-foot neighbor also casts a shadow around it and removes those modules automatically that are shaded on the winter solstice. Now at this point you might be noticing that my lower building still has a height of 0, which by the way is not wrong at all. I could keep it, but if I wanted to spend an extra few seconds, I could give the lower building a height of say 20, and then give my taller building a height of say 70, just to kind of keep the, to sort of have absolute heights. It really won't change the results as long as everything is still the same relative to each other, but now it's just going to look a little bit better in 3D. Totally up to you. That's purely an aesthetic thing. Cool, so now we have our two buildings with the same module but different racking design, and they're different heights so that one is shading the other. Now let's go back to the shading analysis. Remember I said when we did the keep out that the default is keep out from shade. So the default is to calculate that winter solstice and treat that as a keep out. In practice, what we can do is we can actually do something a little bit more sophisticated. So first I'm going to uncheck this box here. So at the top of keep outs, if you uncheck this box, notice that it stops treating this shadow as a keep out. It stops saying that you can no longer have modules that are shaded on the winter solstice from 10 to 2. Instead, I'm going to go to the advanced shading tool over here, calculate the shade across the array, and what we're going to get is a heat map. Now this is based on every module every hour, so it's running through every hour of the year saying where is the sun in the sky. Based on that sun position, what modules are going to be shaded at that moment in time. The weather file tells us how much sunlight there is to be lost at that hour, so that you've got, you're doing all the right things in terms of, obviously you get more sunlight in the summer. You get more sunlight at the middle of the day. So yeah, the shadows are very long in the morning time and the winter time, but you don't get a lot of sunlight in the morning time and the winter time. So what you actually care about is actual sunlight, not just how many hours are you shaded. So in that world, you can see that basically we get this heat map. Now the heat map, these numbers tell you a lot about the heat map. So first of all, the 2.4%, the average shade loss across the whole array, and that's counting both systems, or both rooftops, is 2.4%. By the way, that includes row-to-row shading. So even, it's not only obstruction shading, but you're going to have a little bit of row-to-row shading from one row to the next. Additionally, the worst module is shaded about 23%. So the worst module is losing about 23% of its total potential sunlight due to shading. Now this slider is where you can actually change things. So notice if I move the slider down to whatever, 18%, you can see that we lose these 4 modules here. And this shows you that we've lost 5 modules total. So there's probably some module that's really close to one of the HVAC units, maybe this one right here, and that also is above my 18% threshold. But now, if I go back to this, if I keep moving this slider down, it kind of gives you some intuition for what's going on. As I move the slider down, what I'm setting is a lower cutoff. I'm saying, so at this point, 11.3, I'm saying remove any module with shade greater than 11.3. So if I move the cutoff lower, then I'm setting a lower threshold and I'm removing more from the array. So basically now you can decide really how close or how far you want to be from those obstructions. Not based on one specific day of the year, but based on how much energy does it take for that module to make sense for your system. Now I'm going to go to 10%. We're not an engineering firm, but a few of our customers have started to say publicly that they're using 10% as their cutoff rule. I'm not even sure if that's still the right number because costs keep coming down, so maybe the number is even more aggressive than that. But for now, notice what happens if I do 10%. We're going to remove 65 modules. That's going to be 3.2% of our system. So let's hit that button now. We've removed those modules. And so if I look from the top down, you can see all of these modules here are modules that we would have removed because they were technically shaded on the winter solstice, but they're within 90% of maximum potential sunlight. That's the other way to think about a 10% shade cutoff, is a 90% kind of sunlight floor. And so, as a result, you can often have a bigger system than you would have before if you had just done a more simple shade rule. Now, actually, to Alex's question, Alex asked about deleting one module at a time. You can totally do that. So notice here, if I go to keepouts, you see we've got these two modules right here, and you might look at that and say, that's kind of silly. We would never build that. Let's just remove those. So one option would be to go to edit mode, select this keep out, and drag this corner down. So that's one option. Now, by the way, watch this. I can hit the undo button. So this is actually a whole undo stack. Notice it's actually kept the last few things that I've done if you need to go back a couple steps. So you've got the undo and redo options up here at the top. But the other thing you can do is from the keep out menu, if I just right click a single module, I can remove that one module. So I can unclick, or I can click those guys and just remove those single modules there. Notice also that if you keep clicking it, it just toggles it on or off, basically. So you can go both ways. In fact, the other thing you can do is, notice over here, so all these modules were removed due to the shade optimizer, right? These two, I might say, you know what, if I'm going to get that close to the edge of the building, for structural integrity, I'm going to design all the way to the edge. Watch this, if I right-click right there, and then right-click right-click right here, let me go back to keepouts, I can restore these modules that were removed due to the shading cutoff. So notice what you get really is a nice mix of algorithms and automation where it makes sense, like doing that shade cutoff, and then you can always have space for a human to come in and just clean things up around the edges, just knowing, knowing what you're going to do, knowing the expertise, and knowing what's going to look good for you and for the customer. So, yeah, that's basically the easy way to nudge a couple modules back and forth. So now that we're done with the mechanical, the final step is electrical. Maybe I'll pause for one more moment in case anybody has any questions on that. Cool. So under electrical, now keep in mind there can be a very, very fast solution here. So if I just choose, say, an ABB inverter, notice that basically Helioscope auto-designs the whole system. So specifically, it gives me 26 count of this 22 kilowatt inverter. My string size is anywhere from 13 to 21 modules per string. So basically the inverter quantity is set automatically, the stringing length is set automatically, and I'm done. I could hit save and exit and be done. Now, of course, let me actually go through and talk through what actually happened here. So first of all, inverter count and system sizing. So DC nameplate, right, that's based on the module quantity, is 710. So kind of everything starts with the DC size at 709.6. Then when I choose an inverter, Helioscope it says, okay, how many of those do I need to get as close as possible to a 1.25 DC to AC ratio without going over that 1.25 DC to AC ceiling? So in this case, 26 of my 20 TL of my 22.5 gets me to 585 AC, which is a 1.21 ratio. Notice if I choose a different inverter, say a 27 kilowatt, this quantity drops. If I choose a 20 kilowatt, the quantity goes up. So basically, based on the inverter size, you're going to have the quantity adjust automatically. Choose a one megawatt inverter, and I only need one. In fact, I don't even need the whole one, and I'm only using or I'm only at like a 0.71 ratio. So so that's kind of on the inverter sizing. By the way, you can also override it. So let's say I'm at let's use the chint. And then you want to override it, I can just click the number, it becomes editable. And if I take it to a 28 or 27, if you see what's happening, my AC nameplate is dropping, and therefore my DC to AC ratio is actually going up, which is totally what happens if you down count the number of inverters in your system. So that's on, and then here I'll just go back to automatic and have it just automatically go back to what it takes there. Next, let's look at string sizing. So for the string sizing, Helioscope starts with the nearest ASHRAE location. That tells us the high and low ASHRAE temperatures. That's the sort of ASHRAE min and max. Then the module voltages. We of course have the VMP at STC and the VOC at STC. We can calculate what they're going to do at those high and low temperatures based on the module temperature coefficients. And then we have the inverter's voltage range. Then all of that is just kind of division or multiplication to give us the string sizes for this system. So the one thing I would say there is definitely double check these with the OEMs. Our database is good but not perfect, especially the inverter voltages are often very subject to being overwritten based on where you are or the inverter settings, or they're inconsistent in what they mean by max voltage. So we're great for the 80/20. I would definitely recommend checking with the inverter manufacturers before you submit anything for permits or anything like that. Cool. Oh, and then of course, as with before, you can also set this manually as well. So if you wanted to say, actually, I want all strings to be precisely 18 module strings, you could do that, and now you've got precisely 18 module strings across the whole array. So again, in both cases, you can go as deep as you want to, but it basically is going to give you a very solid answer with zero thinking on the user's part. The one thing I am going to change is notice this inverter is actually collecting a string from the top and a couple strings from the bottom. The way to clean that up is by adjusting my wiring zone. So in terms of Helioscope language, what I have right now is two field segments, which of course you can see the two buildings, and those are both connected to one wiring zone, which is basically one set of inverter and string sizes. But from here, if I create a second wiring zone, I can drag my second field segment down here, and now they're electrically separated from each other. So now, and it's still the same automatic thing. So now in this one, I have 25 inverters because, again, I have a smaller DC nameplate of 612. And then in the bottom one, I have 4 inverters because I've got a 97 kilowatt rooftop here. So basically, just be aware that you've got those as your options for, and then obviously I could choose a different inverter. So with a 97 kilowatt system, I could go with one 75 kilowatt inverter. Maybe I'll add some combiners here. So cool. So now I've got my what do you call it? I basically got sort of a medium-sized inverter here, or very large string inverter, or a smaller like ground-mounted or pad-mounted inverter, and then a bunch of string inverters on the larger rooftop. And then, by the way, we can see all that here in the single line diagram. So here's my single line, which shows me my 25 inverters for the large rooftop. Notice that most of them have 4 strings of 17. 24 have 4 strings of 17. One has a string of 21 and 3 strings of 16. And then for the other rooftop, I've got a mix of 11 and 13 module strings. So basically, you've got this single line, which you can even export that as a DXF and basically have that done there. Oh, good question from Alex. So yeah, what it's going to try to do. So if I go back to, so this one got kind of messed up, but let me go back to my like a regular AVB. It is going to keep, it's going to try to keep the east and west on different azimuths. So if you notice here, let me get it so that I have like individual combiner boxes. What you'll see is so you see what's happening there. This string is basically taking east-facing modules, or northeast here, and then including the next northeast. So when you do have east-west, it is going to do its best to keep those on different azimuths. Although you can, of course, construct a system where you don't allow that to happen just because it's a really small system and it kind of forces them all into one string. So it's not foolproof, but if it can, it will keep the azimuths separated on an east-west system. Cool. Awesome. So that's just a quick note on the electrical side. And yeah, so with that, we're pretty much done. So now let's hit, let me remove those combiner boxes, hit save and exit, and we're finished with our design 25. Carrie, good question. We don't have a way to manually string the modules. The closest thing you could do would be to draw a couple different field segments, since Helioscope kind of strings them up field segment by field segment. So if you did want to control it, you could just draw in kind of sections of the array, and it would string those in order of those sections. Cool, so let's look at what we get from this design 25. So first of all, if I just open it up, here's our bill of materials. Just shy of 2,000 modules, just shy of 19,000 feet of number 10 copper, my 4 strings, or my 20 kilowatts inverters, and my 25 20 kilowatt inverters. Or I should say, I guess I have 4 ABBs and 25 kits, just because I was messing around. And then here's a picture of the array. Notice this picture has a couple things. One, you can customize what's being shown. So at the moment we're seeing modules and keep outs. That's useful if you want to be able to talk through, considerations for maintenance, for codes, for safety, for whatever. You can kind of talk through all the thinking that went into the design. On the other hand, you may just want to show the modules on the rooftop and just get people excited about solar and what it's going to look like. So, notice I toggled off the keep outs. I hit export to generate a new image, and now we have our second image. The bottom line is you can just choose whatever you want to show. If you recall, the earlier one that I looked at had all the electrical wiring. You could do that too, especially if maybe you're sharing it with an electrical sub. And notice at the bottom also, you may be seeing a Helioscope logo here, but you can and should upload your own logo, and that'll show up here right on the image. So, basically that's just a nice touch, because then it actually looks like these images came from you and not from a third-party program. And then finally, we can go to the reports and run the simulation. So here we've got the high-level results, DC and AC system size, all the high-level energy numbers. This is just the flat annual energy production, a couple of the key ratios, performance ratio and specific yield. For the monthly table, the key thing is that you can actually show the table here and copy and paste these out. So if you ever find yourself hovering over and writing those down, don't do that. Just grab these and paste them into Excel. Scrolling down, this table is where you can see all the loss factors that go into the calculations. So basically, you've got your sort of pie chart here, which is the same numbers as the table down below. This helps you troubleshoot if the numbers are lower or higher than you expect. Then scrolling down, you've got the bill of materials and that image of the array at the bottom. Good question from Alex. So basically, yeah, if you have, often you'll have the client's name as the project name and the client's address here, and then those will show up on the report, although not the image itself. So yeah, there's not a way to edit the image, but notice that you can download this report as a PDF. So this is actually downloading this whole thing as a PDF, and then I'll just open the PDF in my browser so you can see what that looks like. Notice, by the way, a small point. Here, if you have your own logo, then it'll actually replace the Helioscope logo in the top corner as well and put your logo there. So you've got your kind of full report here. Cool. And then the last thing is, oh yeah, I was going to show one more thing. So as I said, you can kind of run different iterations. So this could be a variety of reasons. Maybe you're sitting with a colleague and kind of brainstorming different design ideas. Maybe you're sitting with a customer, and maybe oftentimes they might have heard from someone else that suggested a different module, a different design approach, a different whatever, even a different system size. So you can make a copy of the design and make any changes you want to. So in this case, let's say we want to check out a more conservative shade rule, a 5% shade cutoff instead of 10. So I cloned my copy. Let me just rerun that shade cutoff. When it's done, I'll just move the slider down to the 5% mark. Remove again, about 6% of the system size, and then just like I did before, maybe I'll trim a couple, modules off again, just because of kind of buildability and racking, just kind of knowing what's going to work well for the racking. And then electrically, one small thing, if you remember before we had 25 modules for the bigger roof, I now have 23 because we removed a bunch of modules, and therefore since we have a smaller DC system, we can have a smaller AC system. Notice that happened automatically. I didn't have to think about it. It just did it because it was setting the inverter count automatically based on the DC size. Another small example of where Helioscope is it's giving you engineering caliber results with a non-engineer's, with not necessarily an engineer's level of attention to detail. And then so notice here we can see that it's a really nice side-by-side comparison of, yes, I can get more conservative. We sacrifice about 6% of the system size. But the impact on the energy yield, it does improve, but it's only about 0.5%. So for stuff like that, when you want to do different what-if scenarios, it's really nice to be able to run those iterations, see what the impact is on the physical array and on the energy yield, on the physics of the array. So obviously for the net energy, you're pretty strongly better off on the bigger system because that impact of the shade was actually pretty small, 0.5%. One great question from Alex about uploading a CAD file. So yes, you can upload a building site plan into Helioscope. The way to do that is with an overlay. And the basic catch is you have to upload it as an image. So it won't be able to upload a CAD file itself. What you'll do is take a screenshot of the CAD file and then upload that as an image. You just select the file here. It'll show up on your screen. And you can actually upload two different ones. You can upload PNGs, which are JPEGs or PNGs, both of which are just images, right? So here, this is from a drone. So you can see someone, has a drone image of a building. If it's an image, then notice that you could actually edit the image. You can, you can rotate it, you can drag it, and you can resize it. So you will have to make sure that it's sized and scaled properly, but it's a great way to get drone images in. Additionally, or on the other hand, if it's a KML file or a KMZ file, those actually have the scale and location embedded as part of the file, which is why there is no way to edit the location of the KMZ. When you import a KMZ, it's both good and bad. The good news is you don't have to move it. The bad news is you cannot move it. So anyway, those are the two options for uploading CAD for new construction. Awesome. Great questions there. Cool. Any other questions on this stuff? Otherwise, next I'll just switch around to doing a residential example. And like I said, it's the same product, so the Resi one's going to go much faster, but I'll just show a couple of the things that are different when you go from commercial to residential. So starting here again from the top, create my first field segment here, trace out this roof surface right here. And then now I'm just going to choose a module, whatever, Samsung 255. So now at this point, again, my racking type, this is kind of the biggest thing that'll change when you go to residential. So remember the fixed tilt had a flat surface with tilted modules. So basically, if I make this flush mount, then notice it's going to make this whole surface tilted based on the the tilt and azimuth of that array. So in this world, notice the module angles don't change. But whereas before the modules are tilted up, along a flat roof, now they're flush with a tilted roof. And you can see a couple things. First of all, you see the numbers change. Watch, right now that's 20.7. If I take it back to fixed tilt, it's 20.4. It's doing the proper trigonometry of, hey, it's now at an angle. So, that line is longer than if it was purely flat. A couple other things. So let me just clean this up to what a residential would be. I might use portrait orientation. I'm going to take my row spacing down to 0 because they can be, right flush with each other. And then let me change the orientation of the roof. In residential, you actually have two options. You can set an edge as the top or set it as the bottom. In this case, I'm just going to set it as the bottom. Oh, and by the way, Alex's question, yes, let me make the tilt, 45 degrees. Oops, sorry. Make the tilt 45 degrees there. And so now you can see that you've got a, this is what it would look like if you're designing, say, a 12 and 12 roof pitch here. So basically, in this case, sorry, I lost my train of thought. Oh yeah, setting the orientation. So in this case, my sort of bottom edge, my gutter line is the best line, right? And that's how generally it works on commercial as well. The reason we have two options is that we know that there are also cases when your field segment has a really good ridge line, but either no gutter line or a really short one, or it's under a tree. So in this case, I would want to use the top edge, right? Because I've got a really good ridge line. I right-click that circle, set that at the top, and now you see this one's going down from that edge being the top edge. So that's why when you right-click the edge of a field segment, you'll see two options. And in this case, I'll get the same answer between setting this as the top and setting this as the bottom. So it's really not like a material change at all, but it's just, it's really because in some cases you'll have one or the other. Notice in this case, it's a triangle. If you have a good gutter line, no ridge line at all. So now let me just remove that field segment right there. Cool. By the way, Alex, if you don't mind, I'm going to go back to a 25-degree tilt just because I want to squeeze in one more row of modules here that you'll see in just a moment here. So one other thing that I'm going to do here is let me play around with, let me show you a line to click, because that's useful in both residential and commercial. In fact, I used it on the commercial one as well, but it's doubly helpful on residential. So line to click lets you adjust where this whole set of modules starts. So if, let's say I wanted to shift everything here up by a couple inches. I'm going to put my cursor right here. I'm going to right-click, and then I'm going to say Align Modules to Click. When I do that, Helioscope puts the back left corner of a module at the original spot that I right-clicked. So if I want to now move it to the down, right-click here, align modules to click, and it snaps to that being the corner. So I can now shift everything to the left a little bit, to the right a little bit, and notice as I move it to the right, you see I lose that module there. So you're kind of shifting around where this grid goes, and then based on how the grid fits within the shape, it just squeezes whatever modules you can fit within that area. So that's why align to click is very helpful. One other thing that's very helpful here, and it is specific to residential, is manual module control. So check this out. Because your default is portrait, we assume if you want to lay out individual modules, they might be landscape. So if I just click once, I can just add in a landscape module. I can also add multiple ones. So if I click once and then drag to the right, I can add 2 landscape modules there. And then you can even edit them. So now if I select this guy, I can just drag it around. And then finally, if I'm dragging it and I hold down the shift key, it'll snap it into the corner there. So that's what that red line does. I can even multi-select and then either drag the multiple modules. Oops, I don't know why that didn't work. So I can just drag multiple modules here, or select them again and then snap it into the corner there. So you've got some pretty cool tools for kind of manually bringing modules. In fact, here notice if I hold down shift, it kind of snaps this kind of future module and then just click it to lay the module right there. So if you want to mix up portrait and landscape, you can totally do that here as well. Now, for the north roof, let me do another field segment here for this neighbor rooftop. Actually, the first thing that's here that's actually kind of funny is, remember I said Helioscope with 2 field segments always assumes that the new one is just like the previous one. Well, in this case, my new one is obviously facing the wrong direction, which is a big problem in flush mount, but no big deal. Right-click. So again, here, let me just show you from the top down. Another case, I've got a good ridge line, right-click that, set that as my top edge, and now this is facing the proper direction, it's facing west. In this case, let me now do a 3-foot setback for the ridge line for my, for my fire code, 3-foot setback, so now I've got my sort of full 3-foot setback for the top. Hit recenter. Oh, one thing here, let me first, now on this guy, I'm going to adjust with align modules to click to shift everything up. So notice how I did that, just to make sure that I'm starting, as close as I can to that 3-foot ridge, 3-foot setback. Another thing is at the bottom, my alignment here is currently a strict grid. I can select stagger, and notice the difference. Helioscope tries to squeeze in as many modules as it can in each area by having them be staggered from each other. So each row is flexible and independent from the other rows. So in this case, it's the difference between having 23 modules versus 19 modules. So it's a pretty material difference in terms of overall system size there. So now we've got our 2 rooftops. Let's now give them both a height. Oh, notice by the way, the height is the height to the gutter. So at this point, because I haven't set the height is 0. The 0 point is the gutter, right? Obviously, they're not going to go underground. So the height's the lowest point. So let me set them both to a 10-foot height, which really just means that now if I want to incorporate some shading from trees, everything's going to be correct. So let me just add in a couple of tree keep outs. So I switched to tree keep out here. Add a small tree there. That might only be 17 feet tall there. Here, let me add another small tree there. Maybe I'll drop that down to 18 feet. And then for the tree line, I'm just going to draw one big area for the tree line. If you've got a bunch of trees, you're actually better off just drawing the one big tree area and giving that a height. Then, just like we did on commercial, the winter solstice line is often overkill. Instead, what we're going to do is actually calculate the amount of shade that these modules get over the course of the whole year, and then as a result, you can see that our average of 4.4%, max of 12%. If I bring this down to a 10% cutoff, then we've got we're going to remove about 4 modules there. Actually, one more trick here, especially with residential. When I calculate the shading, you'll notice that we also show you, so earlier we were talking about overall shade losses and worst shaded module, but we also have the overall energy production. We have the system size and the energy production. So let's say we know that based on the customer's usage, they can use about 8,000 kilowatt hours. So if I move this down, you can see that energy number is dropping, right? Because I'm removing modules, the nameplate is dropping, and therefore the energy is dropping, of course. So if I take this down to about 8,000 or 8 megawatt hours, you can see that a 6.6 kilowatt system gets me my 7.9 megawatt hours, which is pretty much what I want. So basically, you can use that to set your system size here, and then just like I did before, I'm gonna clean it up. Remove, add, remove, add, just because I knew that all those were above my shading floor, and so now I've got sort of like the right size system with a little bit of human touch to make sure that it's actually buildable in the sort of most convenient, highest production way. To Alex's question, actually perfect question from Alex. Here, let me finish this real quick. If I just choose an end-phase inverter, I am good to go here. So now I'm just going to hit save and exit. So we're done with our design. And then Alex is asking how close the production here is to a sun eye. We have a shade report. So actually, let me, after I run the simulation, let me show you the shade report. Our shade report, so it's right here at the very top. It was available on the commercial one, but these are much more commonly used in residential, and these are used in lieu of a sun eye shading report by a bunch of municipalities, you know, NYSERDA, Energy Trust of Oregon, etc. So basically, these shade reports are doing all the work of calculating your tilt orientation factor, solar access, and the combined is the TSRF calculation. Notice we actually show you the optimal tilt and azimuth. So sometimes people are just curious, what is the perfect tilt and azimuth for this location? They actually show you that here in the footnote, because that goes into the calculations here. And basically, just a quick summary, you know, my south-facing array has about a 3.5% shade loss, but is almost within 1% production of the optimal tilt. My west-facing array has less shade because it's facing west, but it's got a 14% penalty because it's facing west. In net, the TSRF is still solid for both. Then even here, we actually show you the 45-degree perspective view, so you can see the assumptions that went into that production model. So that's the Resi example. Now let me do one more really quick commercial example, one more really quick ground mount system, just to show the couple things that are unique to a ground mount system. And this one is where I'll probably do it in like 90 seconds. So create one field segment here, just tracing out this parcel of land here. Choose a module, doesn't really matter, 350 watt Canadian. I'll go with a 10-foot setback around the perimeter, so I've got vehicle access. The biggest thing for ground mount is you typically want your frame size to be 4 high. So notice when I set the frames at 4 high, each row is tilted 4 modules high. And then we would say, let's make the tilt actually 25 degrees and run the same time of day shading just to have the row spacing set automatically there. So just like that, we've got a basically 5,000 modules, 1.7 megawatt system there. Next, let me do another parcel just to the east. So draw my second field segment over here. Oh, actually, let me turn off those overlays just so those don't show up in my design renders. And then here again, same modules. So now we've got between the two of them 10,000 modules, 3.6 megawatts. Notice this is, you can see how fast this is. I'm just doing this real quick because we're at the end of the time. But you can see it really doesn't make you wait while you're doing it. And then finally, let's pretend that this is actually a 70-foot tall tree line. So I just draw my big tree line, give it a height of 70 feet, and Helioscope, and this is where maybe I do want to do that just fast, 10 to 2 winter solstice, keep things simple, keep things conservative. Great, now I've got a 3 megawatt DC system. If I go up 500 kilowatt inverters, 5 of that 500K is a 2.5 megawatt AC. 2.5 megawatt AC. And then finally, as I move the inverters around, notice this number, that's a 1.7%. That's my voltage drop given the current design. As I move these inverters around, that 1.7 goes to 2.2, then it goes to 2.4, then it goes to 2.9, which then I might say, okay, let me upsize the wires to a 4-aught aluminum to keep my voltage drop, at this point 0.9%. That's the STC voltage drop given how many feet or meters of conductor you've got and what the current and voltage is going to be at STC. So again, 90 seconds to have a pretty darn good ground mount system, at least for a preliminary design, to figure out what are we looking at here, what's going to fit, what's the production going to be, and still have solid assumptions around DC-AC ratio, voltage drop, and the like. Not to mention, by the way, you can get a CAD file. So if I download that design as a CAD file, I actually forgot to mention that on my first design. So let me just really quickly download this as a CAD file, and then here we go. And then here's our DXF. My DXF viewer is kind of old, so it's probably going to yell at me, but actually it typically tends to crash. So at the very least, you can just briefly see this before my CAD viewer crashes. That basically, you get a CAD file for basically 90 seconds worth of work there. Pretty powerful stuff. So that pretty much brings us to the end. Just a couple final notes here. Everything I did is available during the trial period. So you've got, you've got 30 days of as much usage as you can do, and you can literally replicate everything that I just did. After that, it's just $95 per month or $950 per year. So less than $100 a month to get started. 2 months free if you prepay for the year. And then it's per licensed user. If you need multiple users, there's also team discount starting at 10% for 3 users or more. So any final questions for me here? Oh, and Alex, to your question, the easiest way to manually change the production rate is to just adjust the soiling in the condition set. So notice in the condition set, the soiling is basically a flat loss percentage. So if you wanted to make that a flat 7% loss or 8% loss or whatever, this is where you could do that, and then you would see that in the soiling losses. So even for your colleague, if they came in and they saw a lower number, that's where they would be able to go into the production report, and you could actually see. I mean, this is not going to have that higher soiling loss, but where's my soiling? Here we go. Soiling loss, 3% is my personal assumption, but if you had adjusted it, this is where you would see that adjustment showing up. Great. Yeah, so Alex, to your question about the CAD drawing, it's not going to have your title block, so you will often have to drop it into your title block. But yeah, I mean, otherwise it's a fully functional CAD file. Cool. Any final questions for me here? Awesome. Well, thank you everyone for making the time. Like I said, I will send a link to the recording, and like I said, don't be shy about chatting us with any questions as you go. All right. Thanks again, everyone. Take care.